tahu seperti apa variasi unsur pada sampel yang utuh. Nah, maka dari itu, disinilah micro XRF memperlihatkan tidak hanya elemen apa, namun di mana letak unsur tersebut. Artinya, kita dapat melihat distribusi unsur pada sampel yang utuh. Dan micro XRF ini ideal untuk sampel yang non-homogen dan biasanya tidak memerlukan atau hanya sedikit preparasi sampel. Untuk kuantitatif pada micro XRF, dapat dilakukan untuk sampel yang cukup homogen. Kemudian kondisi pengukurannya juga sangat fleksibel, banyak yang bisa disesuaikan settingannya, disesuaikan dengan kebutuhan dari sampelnya. Oke, next slide. Lalu unsur apa aja sih yang bisa dideteksi oleh XRF? Jawabannya adalah tergantung jenis XRF apa. Untuk WD-XRF, range-nya bisa dari boron sampai dengan americium, karena WD-XRF kan dibantu oleh crystal analyzer ya, dan search power X-ray tube-nya juga tinggi. Kalau WD-XRF maupun micro XRF, idealnya dia dari sodium sampai dengan uranium, bahkan bisa sampai americium. Pada konfigurasi tertentu, EDXRF maupun micro XRF yang kita akan bahas ini bisa mendeteksi range dari karbon. Untuk target like element dari unsur-unsur berwarna hijau tua ini, biasanya dianalisa di bawah kondisi vakum. Kenapa? Karena emisi XRF pada unsur-unsur tersebut mudah terabsorpsi oleh udara. Sedangkan untuk heavy element atau logam berat, cukup dianalisa pada kondisi atmosferik, tanpa harus menggunakan vakum. Jadi tidak masalah. Oke. Umumnya nih, loading sampel pada konvensional XRF ini banyak. Bentuk sampelnya juga harus menyesuaikan dengan ring sampel pada unit. Selain itu juga sampelnya juga harus homogen, karena target utamanya adalah kuantitatif. Biasanya XRF ini dipakai di pertambangan ataupun yang membutuhkan loading sampel yang banyak dan hasilnya cepat. Sedangkan untuk micro XRF, target utamanya adalah untuk melihat distribusi unsur pada sampel. Maka sampel stage juga lebih luas. Luas mappingnya pun bisa sampai 19 kali 16 cm dan tidak perlu atau sedikit preparasi sampel. Jenis sampel yang bisa dianalisa juga sangat bervariasi. Bisa solid, powder, liquid, logam, batuan, gelas, maupun jaringan. Itu bisa menggunakan micro XRF. Dan berat maksimum yang bisa dimasukkan ke dalam stage-nya juga sampai 7 kg. Oke. Distribusi unsur yang dimaksud adalah contohnya seperti ini. Warna pada sampel ini merepresentasikan unsur yang ada di dalam sampel tersebut. Oke. Tadi sekilas kita bisa lihat bentuk fisik dari micro XRF M4 Tornado Brooker. Di sini untuk desainnya, letak X-ray tube dan detektor di atas, dan bisa dipasang 2 X-ray dan 2 detektor SDD. Nah, di dalam M4 Tornado ini terdapat 2 live kamera, yaitu di atas dan di pintu depan. Keduanya dapat dilihat dari software, contohnya ini, sehingga kita bisa melihat posisi sampel, dan untuk kamera atasnya juga bisa di zoom dari 10 kali dan 100 kali perbesaran. Kemudian pada saat analisa, stage atau tempat sampelnya ini bergerak searah sumbu XYZ. Untuk X-ray, source-nya rhodium dan dikolimasi atau difokuskan oleh lensa polycapillary. Dan untuk mengoptimalkan analisa, maka dilengkapi juga dengan vacuum chamber. Oke. Bruker Micro XRF M4 Tornado ini menggunakan fitur on-the-fly measurement. Dibandingkan Micro XRF yang lain, fitur ini hanya dimiliki oleh Bruker. Kelebihannya apa? Dengan on-the-fly measurement ini, kita bisa men-track atau melacak bagian partikel kecil selama mapping sampel pada ukuran besar. Cara kerjanya, yaitu diilustrasikan di gambar ini. Ini warna abu-abu ini adalah sampel yang dianalisa, warna pink ini adalah target material yang kita inginkan. Kemudian garis putus-putus ini adalah batas pixel. Nah, ketika stage-nya bergerak pada saat pengukuran, X-ray berwarna biru ini akan memancarkan secara kontinu. Nah, sehingga data yang dihasilkan terkolek secara kontinu dan merata. Dan juga target material dalam pixelnya juga dapat terdeteksi. Sedangkan micro XRF yang lain, X-ray yang dipancarkannya hanya di posisi tertentu pada sampel, sehingga akan ada miss data yang dihasilkan. Dan target material dalam pixel tidak dapat terdeteksi juga. Kemudian, bagaimana sih micro XRF ini bisa melihat distribusi unsur pada sampel? Micro XRF ini menggunakan teknik PTS atau Position Text Spectroscopy pada hypermap. Dengan PTS, pada hypermap ini mampu mengkolek spektrum pada setiap pixel gambar yang dihasilkan. Artinya apa? Artinya kita bisa mengolah data kapanpun, tanpa harus menganalisa ulang sampel yang sama. Jadi misalkan saya mengukur sampel 10 tahun yang lalu, itu masih bisa saya olah sampai menggunakan software. Iya. Slide selanjutnya, di sini saya akan menjelaskan parameter-parameter yang akan mempengaruhi kualitas gambar atau pixel atau hasil analisa sampel pada micro XRF. Yang akan mempengaruhi kualitas gambar atau pixel adalah pengaturan step size. Step size itu apa? Step size itu adalah jarak per pixel yang terrecord. Jadi bisa dilihat gambar berikut. Dari yang paling kiri, step size-nya ini ada 200 mikrometer, kemudian di tengah ada 50, kemudian ini yang paling ujung kanan ini 25 mikrometer. Bisa kita lihat semakin kecil step size, kualitas gambar semakin bagus dan ukuran pixelnya semakin besar. Selain step size, ada juga pengaturan dwelling time atau waktu eksitasi X-ray per pixel. Contohnya gambar berikut, yaitu sampel dengan step size yang sama dengan dwelling time yang berbeda-beda. Nah, terlihat dari kiri ke kanan, semakin lama dwelling time-nya, maka semakin jelas gambar yang dihasilkan. Oke, tentunya dengan pengaturan step size dan dwelling time ini akan mempengaruhi waktu analisa atau waktu mapping sampel. Nih, contohnya pada tabel berikut, sampel dengan ukuran 19 kali 16 cm dianalisa dengan beberapa variasi step size dan dwelling time. Bisa terlihat semakin kecil step size, maka ukuran pixelnya akan semakin besar. Sehingga waktu pengukuran pun akan semakin lama. Nah, dwelling time ini bisa kita persingkat untuk menghindari mapping time yang semakin lama. Oke. Untuk konfigurasi tertentu, kita juga terdapat software yang mendukung untuk melihat mineral pada sampel. Software tersebut adalah AMIX atau Automated Mineralogy System. Jadi kita bisa melihat proporsi jenis mineral pada sampel. Dan konfigurasi ini sudah Batan PTBGN sudah punya di Pasar Jumat. Oke, sampai di sini kalau masih ada yang bingung, jadi micro XRF itu sama kayak ronsen kah atau X-ray yang ada di bandara kah? Jawabannya bukan. Jadi micro XRF ini menginformasikan komposisi komposisi unsur pada sampel, unsurnya apa, unsurnya di mana, dan berapa banyak. Seperti itu. Oke, untuk application example, kalau melihat kemampuan dari alat ini untuk menghasilkan distribusi unsur, maka aplikasinya akan sangat-sangat luas, dimulai dari bidang industri dan teknologi, biasanya dipakai untuk QC, kemudian forensik, life science, geoscience, material science, maupun art and conservation. Oke. Baik, tadi adalah introduction tentang micro XRF. Diingatkan kembali jika ada pertanyaan, silahkan untuk mengajukan di kolom chat. Dan juga jangan lupa untuk mengisi daftar hadir juga di bit.ly/peserta micro XRF. Oke, next session. I would like to invite Dat-Ten Chow and Falk Reinhardt to present on topic what is possible on micro XRF system as complement to SEM, and demonstration software, Brooker Micro XRF M4 Tornado. Please, Dat and Falk, time is yours.
Thank you. Morning, hello.
Hello, how are you?
I'm good. Yeah, how are you?
Good, good, good.
So I think that takes over the first part, showing the differences between, the complement, where microXRF complements the SEM measurements. And I will be then responsible for the demonstration part, I think.
Okay.
Is that right, Dat?
Yes, sorry, I mute my microphones. Okay, so I will start my part. A second. Oh, sorry. Here. Okay, so I will introduce a little bit myself. So I'm a sales account manager in the Southeast Asia regions for the HMPs and XMA units of brokers. So I glad that we have a lot of people that can attend today's, and so I will go to my face to explain how is the difference between microXRF and SEM EDS, and how is it complementary of those methods. So as you know that we have like in the workflow, we have a macro analysis, micro analysis, and the SEM EDS for nano analysis. So for our brand name, we have two type of unit. First is the M4 Tornadoes, and the second one is M4 Tornado Plus. So for the standard M4 Tornado, we can go around from sodium to uranium, and to the M4 Plus, we can go from carbon to americium. So when you think about the micro XRF, you can think this is just a normal XRF, and they have it can be go to a micro spot, micro analyzing spot. So there's two different like a very nature different between two methods. The first SEM EDS use the electron beam as an excitations tuned to excite the elements in the samples, and it has to use the vacuum because of the electron beam cannot penetrate in air. Then also with the electron beam, the SEM EDS will scan the whole samples, and we can see the different particles are there and what are the elemental concentrations in those particles. So, but the other hand, in the micro X-ray, we use the X-ray turf to as an excitation tool to get the signal from the elements in the samples. To get those X-ray beam down to 10 to 20 micrometer spot, we use we use some kind of lens. So there's different kind of lens here. For example, like we use collimators, or monocapillaries, or polycapillaries. In M4, we use the polycapillary lens. So the advantages of this polycapillary lens is we will get the extreme high count rate and better limit of detection of those elements in the samples. So those aspects of the polycapillary will benefit to the mapping function of the unit and provide a higher resolution elemental map in almost 10 times shorter measurement times. So in the micro X-ray, what we really do is, you can see in the slide, we can put in this case is glass bottles, or we can put there is the something here like a drill core for geological samples, or even powder, and even like a fresh leaf. Out of that, so if you are using an SEM EDS, you put something like a wet samples into the chamber of the SEM EDS system is something like impossible. I will explain this later on. Also, we can put there like 5 sections, some samples that you are really familiar when you're using the SEM EDS. So the result come from the micro XRFs is elemental concentrations and mapping in the elemental map. So for the micro XRF, we can use a single point or multi-points to get the concentration of the elements in the point we choose, or even we can use as a light scan to see the difference from sector to sectors in one element or multi-elements, really up to use. Or we can do area mapping. So you can see here in the area mappings, the elements is highlighted in a different color, so it's very easy to see. And even though you can choose one of those elements and highlight it with lowest or highest concentrations. So now we go to the important things here. So this is the difference between the SEM EDS system and micro XRF system. First is the sample preparations. So by the natures of the method of the SEM EDS, you have to have conductive samples. But the case is most of the samples we are analyzing are not conductive. So you have to make it conductive. So therefore, you have to coat the samples, for example, like using carbon or gold coatings. So after that, you can put it into the chambers of the SEM EDS for analyzing. So this is by the natures of the electron beam, because it will judge the samples without coating, without conductive layers, and it will never working as an electron beam. So in more important things is the SEM EDS system have to working under extreme vacuum environment. It simply by the electron cannot penetrate effectively in the air. So Now the consequence of this vacuum environment is that you cannot put any kind of wet samples like a fresh leaf, like a piece of meat, or some liquid samples into the sample chambers. So under an extreme vacuum condition, those samples will be dry and boiling itself. And the most important is when you put something wet into the chambers, you will contaminate the detectors. So, but in the other hand, with the micro X-ray, you are free to put any kind of samples there. So you can put there the wet sample, liquid samples, or the big block samples, or for example, like a glass bottle or some things. And the unit can even measure those heavy elements like arsenic, lead, cadmium, or something like that in air with a vacuum, even though for those units we have an adjustable vacuum. So in case that you need a vacuum environment for light element like carbon, oxygen, or sodium or some things, you can use the vacuum for analyzing. So okay, so the other things in the SEM EDS, because of the SEM EDS use an electron beam as an exciting tool. So if you there's a big disadvantage there because of the electron beam cannot penetrate down into the samples. We are talking about like nanometer to 1 micrometers in depth. So it means that all the atom beyond this spot will be undetected. On the other hand, when we use an X-ray, it will penetrate deep into the samples. Of course, it will really up to the elements, the heavy elements, the layers, and many things else. But in general, it will be deeper. It will be deeper than the electron beams. Yeah. So which you know that when you have an penetrating test, so you can see some elements, some elements, some other elements inside the sample in some in some applications. So which means with the micro X-ray, you can also analyze the coating thickness of the samples. You can measure the depth of each layer in multi-layer coating samples. For example, this is a normal circuit chip. We analyze it with the micro X-ray, and because of the X-ray beam can penetrate through the thin layers of plastic and ceramic. So you can also see the gold point there in the samples, which is impossible to the SEM EDS. Also, we have some examples for the elemental mappings. So on the left-hand side, we have here is the elemental mapping from the micro XRF, and on the right-hand side, we have the elemental mapping from the SEM EDS. You can see that in these white rectangles, we can see some copper details in the solder part. And from the SEM EDS, this is like invisible to the SEM EDS. Also, for the second examples, the same things happen to the barium, gold, and aluminum inside. Sorry. Okay, so here we have the we have compared the elemental signals differences for the solid elements. So you can see especially when we go to the heavy elements, we have a really much better signals than with the SEM EDS. You can see this in the blue one is the SEM signals, and the red one is the micro XRF signals. This is not mean that the SEM EDS has a bad excitation source. This is only because the SEM EDS using electron beams as an excitation source. Therefore, the sample volume is smaller. The area where it can penetrate into the samples is smaller, and it has a drastic difference in intensity for different elements. We can see here. Also, here is the limit of detections. So follow this, we can see that for the light element is the limit of detection of the SEM EDS is quite better than the micro XRF. But if you go to the heavy elements, this I can assume that it's calciums. So it's like 1 time better in the limit of detection. So also there is some other difference in the maintenance between those methods. So the SEM EDS will require very strictly in the working environment, like clean room and anti-vibration environment. Also, because of you have to make a conductive sample, so it will lead to the accessories and the consumables will require test. Even there is some maintenance for those accessories also, and the operations is quite complex compared to the micro XRF, and always have require high skill and experienced users to operate. On the other hand, for the micro XRF, there is no special maintenance is required. This is a bent-up type and is high mobility. For the vacuum, we use the oil-free diagram vacuum pump, so it requires no maintenance there, and it's really easy to operate. But in the conclusions, we are not saying that the micro XRF will like completely replace the role of the SEM EDS system. They are complementary technique. So with the micro XRF, we will get the overview of the elemental distribution informations on a very large area of samples in a very short measurement times due to the high speed stage and the high excitation and density. And and from that result, we can identify the interesting or specific areas for additional technique, like the SEM EDS or higher resolution analysis scales. So most of the case that this is a little bit outside of the discussions, but most of the case from our customers, they will prefer in their workflow micro XRF system and also SEM EDS systems, because it's really saves time when you can do the mapping, elemental mapping with the micro XRF. Okay, so that is all my part. So we now can move to the instrument demonstrations with Bob.
Okay. Well, thank you. So since I want to show the instruments and some of the samples and also how to operate the software, I cannot do this sharing my screen, but I do have several cameras attached as my webcam, so to say. So in the screen, or in my video screen at top right, you can select to pin this video, and then you get it full screen. So you will have a better chance to see me like this. Yeah. Okay. Let's start with the instrument. So we have in our lab here both versions of the M4 Tornado. That's the normal standard M4 on the left side. I hope you see it on the left side. I'm not sure it's mirrored on my screen. And on the right side, we have the M4 Tornado Plus. So from the outside, they look pretty much the same. Only the door is a little bit more modern, looking at the M4 Tornado Plus. Apart from that, the differences are small. So this one, the Plus is optimized for detecting light elements, and by that we mean elements below sodium. So the periodic table, sodium with atomic number 11 is what we can reach with the standard M4 Tornado without problems. And if we want to extend our measurable range to the lighter elements, we need to, above all, change the detectors. You know, also from SEM, there is these the light element detection, the light element windows, and that's what we then employ in the M4 Tornado Plus. But also the tube and some other small changes needed to be made to optimize for light element detection. It's still, as Dat just told you, below calcium, the limits of detection are still better with an SEM than with a micro XRF. It's just, we can measure so many different samples with these instruments that sodium was a limitation, and we somehow overcame that. We say that we can see carbon, and we can see carbon, but really for quantitative analysis, we start with oxygen. So oxygen and fluorine are the main elements which we can handle with the instruments now. So here's a selection of samples which we have, or which we usually measure. So there's small electronic components which may be interesting for quality control, but it's more for research purposes. We do have drill cores. So this is a normal sized drill core which fits the instrument stage quite nicely. So to show you, this is the instrument stage. It's a plastics table. So plastics table, which you can take out and put into the instrument. There is a frame here which shows which area can be measured. And this is 20 centimeters from left to right and 16 centimeters from top to bottom. So yeah, this is 22 centimeters of drill core, which can measure it almost fully. Also larger hand pieces of rocks. So you see, this is just as you find it in the field, can be placed. You don't need to be especially extremely cautious with touching it. Micro XRF, as it is not so sensitive for the very light elements, usually does not have a problem with normally handled samples. So yeah, we also have Chinese coins over several centuries, which can be used for provenience analysis. So the method can be used for provenience analysis. Here we have a some special dagger, ceremonial dagger, where the composition of the metals may be of interest. There's also leaves, so ginkgo leaf and some wine, I think it is. And here, this is a freeze-dried potato. So, so you see the range of samples which can just be put in is quite high. So there's another set of electronics, especially here the coating thickness usually is of interest. So the goal, as Dat also already said, with the X-rays penetrating through large portions of our samples, we can measure thicknesses or look through the coatings and see what is beneath. For example, checking the quality of the solder bumps with which the ICs have been bonded to the supporting. Here are some glass samples. So they are just standard materials. Lots of our customers are from the field of forensics, and their glass analysis is a large field. And something which we did recently, maybe I can show you closer. So this is a faded photograph. You see the paper turned yellow, brownish, and the black picture also got more brown than it used to. And this faded photograph, you still see that. So this is a scene from a harbor. So you have a ship here, and there's a horse carriage there. What you can do with micro XRF, so even though the picture is faded, the silver is still where it should be. So if you just measure the distribution of the silver on that sample, you can reconstruct, so to say, these old photographs. We just starting with doing this on a larger scale until now, more testing. And here there is also some larger part to measure the zinc coating on this metal piece. So again, so for quality control issues, you have to find a surface which you can nicely access with the instrument. And for example, here in this region, we can easily access and measure the thickness of the zinc. So what we also have here is our sample holders. So I don't have any thin sections here at the moment because all my colleagues who are from the field of geology, they are not here at the moment, but this is our thin section holder. And what's missing here, or actually here we could place a holder for the drill cores to have the surface of the drill core exactly at that same surface as the thin sections. So then you can measure them or put them in at the same time and measure them maybe from with a remote connection to your instrument, and don't have to take care about any possible difference in the Z range, because the samples should be in a similar height to be measured. They don't need to be perfectly in the same range, but we do have a crash protection in our instrument. I'm not sure whether you can see it from here. Maybe you can't. That would be difficult to do. But we have like, a centimeter between the roof and the crash protection. And then there's another half a centimeter between this crash protection and the plane where we want to measure. So samples cannot be completely of a different height. They should be arranged in a way that they are in the same plane. If you only measure, or if we only measure thin sections, we usually just put them on our plastic table. We place a rubber mat, silicon mat from bakery shop or something. So you can just place the glass tiles and they won't slip because the acceleration of the instrument is quite high. So if you do not place the rubber mat, then the samples may slip back and forth just because of the acceleration. Today, I would just quickly put in two samples. This is a granite tile, so just from the field of geology, and there's an electronic component where we can see how we can look through the coating. And as you see, I just take them and place them in the instrument. So this is, I place them a little bit apart, again, a rubber mat, so that we can access them both. They have different height, so I just want to make sure that they do not cause a crash. So you load the instrument, and then there's this button, like with the iPhone, you press the button in the center, and then you can start. You see here indications for 2 X-ray tubes. So this instrument can be equipped with 2 X-ray tubes. The first one is the one with the micro spot, so the 25 micrometer lens. And the second one comes with a collimator or collimator changer. This is because due to, maybe we see it in the spectra later, we have some artifact coming from the tube material. So if you use a rhodium tube, we may have difficulty, or we will be having difficulties measuring rhodium and some other elements, in this case, technetium, ruthenium, maybe some palladium. And just to widen the range of applications, there's the second tube, in this case, a tungsten tube, which causes problems in a different spectral region. So you can choose which tube you use for the specific task. Door is closed. If I evacuate the system, then I will be having here a blue light. Oh, you can see it over here already. So this one is pumped down. You see there's a blue light because this one is under vacuum now. I will just quickly go over here. So the instrument is controlled, can be controlled completely by the software. Even opening and closing the door is a button in the software. So I can, with clicking here, also open and close the door. And there's another button for the vacuum. Let me quickly, so you should be seeing that now. So here is the door button, and here's the vacuum. And I press this button now. I don't know. Yeah, so, and you see that it's pumping. I can select any pressure between 800 millibar and 2 millibar with the pump. So if you have a liquid sample, for example, where you know that you want to have some, for example, sulfur in an oil, so you want to evacuate a little to get a higher sensitivity for the sulfur, but you cannot evacuate down to 20 millibar because the vapor pressure of the sample is because then you would reach the vapor pressure and the sample evaporates. So you can select a pressure of 500 millibars, for example, and then the pump goes there. So this is a little more flexible than the SEM, because also, as Dad already told you, the electrons in an SEM, they will not be hitting the sample, or at least not in the small spot you want to have if you are measuring in high pressures. So yeah, that's why this is a nice thing. Usually, so if with the M4 Tornado, the normal one, you measure at 20 millibar, because all the elements which are affected by this small pressure, in our world, small pressure, we don't see anyways. So carbon, oxygen, nitrogen, those elements will be absorbed by the air in 20 millibar. But we don't see them anyways. So we just stick with 20 as a standard measurement condition. And you see after 1.5 minutes, maximum 2 minutes, we have reached that pressure, and then the pump goes silent again. I don't know. So you will not be hearing it now, but the pump only pumps with a noise until it reached 20 millibar, and then it's silent, or it goes silent. And silent, and then only after a couple of minutes you have tuk, because it's compensating for the leakage rate. But now you can work next to the instrument. Also, it's a full protection unit, so you can sit next to it and measure, so there's no radiation coming out of it. And so it's user-friendly with that respect. And now let me quickly show how to operate the instrument. So this is from a measurement earlier. So don't be confused. So we don't have this sample in here. What you see down here is we call it overview camera. So it's a fisheye camera in the inside of the door. And you see the two samples I placed. So there's the granite tile at the left, and there is this coating sample at the right. Here is a screen looking from the top, or the camera looks from the top. It's called 10 times magnification. Has a field of view of roughly 1.5 centimeters. And we also have a 100 times magnification with a field of view of 1.5 millimeters. So I use this one for pre-aligning. Instrument is operated with the mouse mostly, so I have these rubber different icons to, yeah, for example, move into Z. And the longer this arrow, and the faster the stage moves. There's also the option for autofocus, but yeah, let's see them. So there's also a rubber band for moving in X and Y direction. So I'm here now on the granite tile, and after, yeah, pre-aligning it for Z, I go to the 100 times magnification and press the autofocus, for example, and then, yeah. So you see that the stage moves the sample through the optical focus, and then if this focus is found, we, yeah, are in the plane where also the X-ray lens has its focus. So the instrument is aligned in a way that now, when the optical microscope sees a sharp picture, also we are in the zone where the X-rays have the smallest spot, so the 25 or sometimes even 20 micrometers. So the lenses are, yeah, have some variation. So I think we guarantee that we are below 25 micrometers. Some of our lenses are even 12 micrometers spot sizes. But yeah, so, and then driving around the sample, and you see that our field of view is not sufficient to completely see it. So I have the option to mark an area on the stage and create a mosaic image. And then several pictures are taken. And from this, a composite picture, so a mosaic image, is stitched together to get more overview. So you can do a mosaic image of the whole sample stage. So the 20 by 16 centimeters. And with this mosaic image, for example, I can show you, if I click on a location here, you see that the stage moves there. So this image is not only an image, but really, yeah, allows you to navigate for your samples. And so aligning also is pretty simple or straightforward. With some experience, it takes about the same time as the pumping down. So aligning a sample is the same 2 to 5 minutes as evacuating the chamber, just 2 minutes. Also, you can manually focus. Yeah. So and here we have a sample where several structures are on it. So 0.8 millimeters, 0.6 millimeters, 0.4, 0.2 millimeters for some resolution testings. And yeah, you see, this is a gold sample. And if I just quickly take a spectrum, we will be seeing, of course, signal from the gold, which we have here. So let me add the gold. We were expecting this, but we also see other elements in the sample. And this is because it's a layer system. So we see nickel and copper, and maybe even palladium, I don't know. So some of these samples do have, yeah, palladium as well. So we have a gold layer on top of a palladium layer, on top of a nickel, on top of copper. And this one is on a bromine-free PCB. No, there may be some traces of bromine, which we still see through the sample. So, I mean, these layers are not thick, usually in the 50 nanometer range. The gold is in the 50 nanometer range. Palladium maybe 100, nickel 2 microns, and then there is some, yeah, say 5 microns of copper as a wire, so to say, and below that is the PCB. And we see through all of this with our X-rays. So the electrons, I don't think they would pass the gold layer because gold is a heavy element. 50 nanometers of it. You need high electron energy to pass through it. Yeah, so even though we pointed out the differences between SEM and EDX, in the end, it's very similar. So we get an energy dispersive spectrum where we identify the elemental lines. Only the SEM usually works in the regime here from 0 to 10 keV, and we usually work from 1 to, say, 30 keV energy. So if you have experience with the SEM, you will find your way around the XRF spectra. Only this penetration into the sample is the main difference to keep in mind. Apart from that, so I just showed you a point measurement. So I went to a position and pressed this button. There's also multi-point measurements. I think this is also something very straightforward. So I can select different locations. Okay, I need to. So different locations where I can place samples, and if I then press acquire, I will be recording several points on that sample, one after another. We do have a line scan mode where you can create a line profile along your sample. Let's quickly here, and I can position it any way I want. In this case, I want this one, and 10 cycles. It is set now. I start. Usually, or our software always records all the spectra per pixel. So it's called hypermap, or we call it hypermap. It's a position tagged spectroscopy. So you don't need to know the elements before you start the measurement. You can also select them while the measurement is running, or even in a saved data set. So it's not like WDS, where you have to know before. But energy dispersive, all the spectra being saved, you can then later access the data. And here you see, so I'm now running at 100 micrometer distance. So the 200 micrometers really has just one step here. And you see then going wider and wider. So pretty straightforward line profile. And of course, we have the area scan. So mapping the sample for the elemental distribution. So again, so I can align the edges where I want them to be. And in this case, for example, the 50 micrometer step width, I can decide time per pixel. Our instrument is measuring on the fly, so we are not going to a point, measuring it, going to the next, measuring it, going to measuring it. The instrument moves continuously, and then we tell it how long it shall take to cover a distance of 50 micrometers. So 50 micrometers within 10 milliseconds. So this is now what we make our measurement time. And if I then press the acquire button, the measurement starts. So you see here in the software, the shutter for X-ray tube 1 is now open because I'm measuring with the first X-ray tube. 2 detectors I have in my instrument. Both of them are collecting data now. And clear the data and select the gold, nickel, and copper that I'm expecting. And so it should be seeing something over here. So you see that this is the bar of the X, and you also see how long it takes. In this case, 5 minutes to cover this area of, quickly check, 12 millimeters by 4 millimeters. And this is because I selected 10 milliseconds per pixel. I could also measure this with 1 millisecond per pixel, or measure it with 100 micrometers per distance. So I could save time even. But measurement of this quality would already allow us to quantify the layer thickness and give us enough spatial resolution to clearly see the structures in the sample. So even if we have also this rather fine structure, we will be seeing it without problems. in larger samples, like for example this, you usually wouldn't scan the whole thing with 50 micrometers per sample. You could, but you wouldn't. First of all, the surface is not flat. So if you put it in, you will be out of focus most of the time. You will not be losing any information, only some spatial resolution. So you don't need to scan a sample of this shape with 100 or 50 micrometers resolution because the spot is so much larger, but you could. So yeah, overall, micro-XRF is a method for pre-screening. So many of our customers use it for putting the samples in the micro-XRF first, because as you see, you can take it just like that, put it in, measure it. The X-rays will not damage it. So X-rays do not do damage, especially not to rocks or metallic samples. There may be some coloring in the glass, but this will fade over time. So this is some temporary effect. But yeah, so the X-rays don't hurt the sample. You don't need to prepare them. And after you measure them and you have a good idea where your spots of interest are, you can then mark them and go to, for example, the SEM or for an ICP-MS if you need the higher element sensitivity. And so you can save a lot of time by first putting it in, identify the areas that are actually of interest, and then go to the higher resolution or higher sensitivity methods, or the destructive methods, like for example, an ICP-MS or some other sort of sample preparation, which you do not need before you scan it in the M4 Tornado. So so this is then the result. So not a picture, but really the elemental distribution of my 3 elements. So this is the gold, this is the nickel, this is the copper. In this case, they are all at the same place because it's the layer system has been designed like that. If I have areas like this, can cut out individual parts because, as I already said, we are saving every spectrum for every pixel. So I have object 1, which is on my layer system. Linear scale. So object 1 in green here is my layer system. So I see the nickel, copper, and the gold. And object 2 is the PCB, where I mainly see the bromine peak as a flame retardant over here. So pretty simple. Ultimately, in the interpretation of the results may need some experience and also some knowledge about the sample already. Because sometimes just from the spectrum, you cannot say whether this is a layer system or an alloy. There could maybe be a white gold with copper and nickel and gold, and you couldn't tell it apart just from the spectrum. So you need some prior knowledge about your sample on your sample to properly work with the data which you received. But let's wait this 16 seconds still, and then I can show you maybe some loaded data, something else which you can do with the software. If you have a Bruker software for your SEM already, most of the options you will find here again. So we save this PCB printed circuit board, save it. For example, if I open, for example, this granite tile. So I measured the granite tile which I placed on the other side of the instrument, but in this case with 30 micrometers depth size and 30 milliseconds per pixel. So the whole measurement took 6 hours. Usually this long measurements can be done overnight. So you can place 1 or 2 samples of this size. So they need to be at a similar height. And then you can measure them in one run overnight. As I said, the instrument is full protection unit, and it's definitely safe from a radiation point of view. Yeah, so this granite tile here, you see the elemental distribution of the silicon, so quartz rich and the feldspar rich. There's the aluminum, the potassium, calcium, and so on. If I select these elements, I can do phase analysis. For example, so the software tries to sort the pixels in your map according to the intensities of the selected elements. So I quickly toggle between map results, where you see, so blue and red as a mix will be pink. There's the blue, where you have calcium without the aluminum. Yellow is the silicon and the aluminum, and so red, green, and yeah, so the red, green, and white. So this is mixed colors. And now this one is sorted into phases, which have this very similar distribution. But I can look, for example, for the phase 2, the green phase here, and I can create the sum spectrum of all the pixels, which will be found to be in this phase. So phase 2 is relatively lots of calcium and yeah, silicon. So with some tweaking the parameters, you can get to a point where you can, in this sample, for example, tell apart the feldspar-rich, the calcium potassium-rich feldspar and the calcium-rich feldspar and the quartzes and mica maybe as well. So the main components of the granite. Also, what you can do, or can make the software do, go through the whole data set and calculate and find hotspots, so to say. So it's now, the software is now going through all the pixels of the map and identifies for each channel what was the highest count rate which you found in this channel. And like this, you can identify elements which are located only in very small areas, so that in an average spectrum you will not be seeing them. So you need this so-called, we call it maximum pixel spectrum, and usually, so you can use it to find some hotspots. So while this is calculating, maybe something about this instrument, but yeah, I think I told you we have two spectrometers. They do have independent signal processing. So really, you get twice the count rate. So it has double the area, the active area of the one detector, but also double the pulse throughput. And yeah, so now this one is finished. I can have a look. So let's get rid of letters. This maximum pixel spectrum can have an auto identification and see which elements found by the algorithm. For example, if you see here uranium, quickly check whether there really is a peak. Sometimes software identifies some noise, maybe. But in this case, the uranium peak, I think, is true. So maybe also there's some thorium, but let's focus on the uranium, which we had here. So this is obviously a trace element in our sample. So it's overlapping now a lot with the scattering. So where you have quartz, it's a rather light matrix. You have a lot of scattering background. So we need to check the so-called deconvolution. It's also called fast deconvolution in our SEM, I think, software. So we really get a background subtraction and also the reduction of elemental overlap. But yeah, so you see now the background is reduced. I could also average over larger amount of pixels. Another trace element in this granite is niobium. So yeah, the sensitivity for these heavy elements in traces goes down to the 10 ppm range. And so if you would be measuring one spot for longer times, you can get to the single ppm region, single digit ppm regions for these elements here: rubidium, strontium, yttrium, zirconium, niobium, molybdenum. So they are very effectively excited by rhodium. And yeah, so these elements we can get to single digit ppm detection limits. So if I, for example, cut out that area where we have a higher intensity of the uranium, this may be a diffraction more than actually uranium peak. So this is another thing which is different between SEM and XRF. So in this spectrum, you see, so the zinc, for example, has an odd shape here. So there's a triangle shape below the peak. This is diffraction. And diffraction is an effect which you may know from XRF. It's used with XRD, so X-rays are diffracted at crystals. And in XRD, you make use of this effect and really determine the orientations of the crystals or this crystal type. In our case, this may be a silly, so granite is formed of minerals and these are crystalline structures. And here we see, yeah, diffraction overlapping with the zinc. And here's also prominent diffraction peak, so very broad shape. And I think this triangle shape here with the uranium region of interest is also diffraction. So that was not what I was looking for. Averaging over a larger area. Again, not. So yeah, interpretation of the data then needs some experience. So from the maximum pixel spectrum, I know there is some uranium. This is a proper peak, but I don't find it. There may be one. So there's peaks. Yeah. All right. So this is some of the ways of mining the data after you have collected it. Again, so this was saved, measured last night. I saved it. I did some other measurements in between. Now I opened the data block and I can do everything as if the sample was just in now. So identify new elements and look for, yeah, in this case, searching for the uranium, which I do not find. Maybe niobium is more rewarding. So this, if I select this region, there's my niobium peak. Yeah, so I do see clearly peaks in that region, more easy to find. So the niobium is easier. And yeah, I'm not aware of the schedule and whether we already reached the Q&A or yes. If there's questions, maybe directly related now to this part.
Okay, so the demonstration finished? Sorry.
I could go on, load different data sets, but I would know. So if you have questions or want to have more details with respect to this and that, I can do that.
Okay. So bagi para peserta, kami memberi kesempatan 1 atau 2 orang yang bisa langsung untuk bertanya kepada Falk Reinhardt. Silahkan kalau mau ada yang bertanya, bisa lewat chat. Oh, saya mau bertanya, nanti saya open mikrofonnya. Yeah. So I give a change to the participant can ask question directly, but I actually have already collected the question. So yeah. Okay, sorry. Yeah. So, yeah, can you see my screen? Yeah.
Yeah.
So from Professor M. Badarudin, Yeah, for solid metal sample, is it necessary to prepare a smooth surface? So I think already explained.
No, yes, depends on what you want to do. So in general, we always say that you do not need to prepare the sample, or very little sample preparation is necessary. But so this is a copper sample. It's cast in epoxy, so they've been cut.
Yes.
I don't know whether you see it, and they are polished. So these are standard materials, and for quantitative analysis with very high precision, this smoother is better. We could measure them, so you can measure samples just like that. You will get signal, you will get elemental distributions, but our quantification algorithm, so we do have to quantify, I don't know whether you see it, so we have this quantify button every once in a while in our, or actually in every workspace, you can quantify spectra. This is an FP quantification, and the model behind it wants a smooth surface. And so the results will be better if you have a smooth surface. Yeah, so you don't need to, but it's better. I think that's the answer. Okay. So the second question is the thickness and the surface contour effect. I cannot see the end of the line because there's the video image is there. And so if you could read it aloud, it would be nice.
So, the second question is, how does the thickness and surface contour affect the micro XRF?
So the micro XRF.
Oh, sorry, I'm being muted.
Okay.
Sorry.
Yeah, no problem. So the contour, do I have any example of a not flat sample? I do have images, definitely. So maybe you can.
Okay.
Yeah.
Should I stop?
Maybe you can yeah, if you.
Yeah.
So this is a really a crystal sample. So really you see the feldspar and the quartz crystals really sticking out of the focal plane and everything. So this is a coarse sample with topography in the centimeter. So let's say 1 centimeter is the difference in height here. So, and you see that everything which is not in focal plane looks blurry, like with an optical image. But you do see the sample. And now so everything which is not flat, as we just discussed, so you can still cut out parts of these sample, also of the map, and quantify. And even if you have a coated sample, you can do this. So measuring is okay. Pressing the quantify button is also okay. And the result will be better the more you have a flat sample. And if you have differently thick layers, maybe I even have a data set for that. Open. Let's see if this loads quickly. So this is a coated glass sample. So you have glass in rectangle, and there is metal coating left and right. And this coating was aluminum and copper. And you see, maybe a little the gradient in the aluminum intensity. So there's the part which is not coated, and you see that it's a little bit darker up here and a little bit lighter down there. So aluminum gets more from left to right. Copper is vice versa. So it's difficult to show this maybe with false colors. Sorry for the clicking. So you see now blue to yellow. So there is also a gradient from left to right. We are, in this case, shooting through this, the sample. And you see, the thicker the layer is, the more signal you get.
I see.
And this can be quantified. So we do have an additional software for layer thickness analysis. It's called XMethod. And then you can really quantify the thickness of these layers. Usually we say up to 30, so 30 micrometers is the thickness through which we can shoot through with our X-rays. So most coatings nowadays, so even of these massive parts, are below 30 micrometers. So we can measure many thicknesses because we shoot through the whole layer.
Okay. I see.
So it does not really affect the instrument or anything, just needs interpretation.
Okay, I see. Okay, so the next question is, what are the advantages of micro XRF when compared to ED-XRF and, sorry, I think this is could be WD.
Yeah. WD. Okay.
Yeah.
So micro XRF is, so we do energy dispersive XRF, so it is an ED-XRF. Our advantage is the spatial resolution. So again, here, this is a potato, for example, freeze-dried potato I showed before. I don't know whether you can see it, but you have the spatial resolution. You have the spatial resolution to see where the elements are. So with the normal XRF, you would get the average of all of it. You will be seeing the same elements, but you may not know where they are. So the spatial resolution, like in an SEM, is the advantage over the common ED-XRF, and WD-XRF usually the same. It's also a large spot, so you would average over the whole sample. Of course, you have the better resolution for elemental lines, so you have almost no problem with overlap. But again, so WD-XRF is, I think, more different to what we do here than SEM EDX. SEM EDX is much closer as a method, and WD-XRF is really, large scale, high resolution. Also, what we do, I didn't tell you. Maybe I can quickly. The tubes here, they are running at 15 watt. So not kilowatt tubes, it's 15 watt. 15. So the maximum I can give here now, so this is a 30 watt tube. So it's like a light bulb. So this is also a difference to the normal WD XRF and also ED-XRF instruments. They have kilowatt tubes, so it's 30,000 watt. This is a light bulb. So power consumption is much lower. Also the lifetime of the tube is much longer. These tubes do not age. So it's not a consumable. So the instrument, you can work with 10 years without changing the tube. Maybe. So that's not a methodology difference. It's just a difference in the hardware.
Yeah.
Because we focus our beam, don't need the high power.
Okay. Next question is, can micro XRF be used portable? How to check accuracy of the result?
So we do sometimes take the instruments on a road show, so travel to another country with the instrument in the trunk of the car. So we do not do that much anymore, but we used to. So it can, when handled carefully, we can you travel with it. And also we provide these, sorry, it's not cleaned up properly, but you see this box. This is a flight case. And where this instrument is fixed to that case, the computer and the pump, okay, the pump just now is not, but usually the pump, you should see here, is also in that box. The computer monitor can be strapped also inside, and then you can take this and travel around. And this is rather stable. So when we go to conferences and exhibitions, we use this flight case setup.
Yes, we actually did it 2 years ago in Indonesia. Yeah.
and then we do have some standards. So we usually take a glass standard with us, and also a metal standard sample. So not a certified reference material, but a material where we know what the instrument gave as result before the travel. And this can be compared then to after the travel and to check for the accuracy. So measuring a spectrum for 2 minutes and pressing the quantify button. And if we get the same result, nothing happened. And if the results changed very much, then we need to recalibrate the instrument. This, for an experienced user.
Yes.
It's also a thing it takes, let's say, an hour to measure pure elements. So all our instruments come with these pure element plate. So where you have a set of pure elements which you can measure in your instrument, and based on the spectra of these samples, the instrument can be calibrated in the field. But usually it's not necessary. So if it didn't drop, then the arrangement is quite stable. But I think it likes the lab a bit more. So air-conditioned environment without someone hitting the table all the time, I think is better for the instrument, but it is used a lot for traveling around roadshow instrument. So, no.
Okay, sorry, being muted again. So the next question is, what is the minimum power requirement to operate the micro XRF? I think you already explained. And is there any problem if the sample is kind of synthesized magnetic materials, because it made some interaction between X-ray source with the sample?
So the X-rays will not be affected by the magnetic field. That's not a problem. So again, electrons, they will, since they are charged particles, they will circle around in the magnetic field and maybe never hit the sample, at least not at the position where you think you are. The X-rays are not affected by magnetic fields, so you can do that. The only difficulty may be that some of the parts inside the instruments are metallic, and the magnets may stick to that. So especially our crash protection is a metal part, so you would need to unscrew. So if you have strong magnets, which have a large range of sensitivity, so then you may need to fix them somehow, or unscrew the crash protection. Then you don't have magnetic parts anymore. So we did that already. We measured magnets. What you can do is, usually in a magnet, you are looking for the, say, there's some rare earths and some metals, of course. You can place them under a thin plastic foil. So you just cover them and fix the plastic foil so they cannot go up. And then you can measure, so the X-rays will also go through the plastic foil without problem, and the signal comes back, and your magnets cannot attach themselves to the inside of the instrument. So magnets work. I think we even have a magnet manufacturer as a customer.
Okay. So the next question is, how the micro XRF technology for detection carbon? Is it XRF?
No.
No.
So the problem is, so we will be seeing carbon in almost every sample because at some point, so okay, the way we handle the samples is not very clean, of course, not of course, but as you have seen, just touching them, this covers it with carbon. And even though so the X-rays have lots of penetration depth into the sample, the information depth for carbon is not much more than with an SEM. So we stick to the first 100 nanometers. So it's a surface signal. We will not be seeing carbon inside a sample. We will always see only the surface. And we do have the problem may not be, but so this is not an M4 plus now. So the spectrum stopped earlier. So with the normal, with the M4 Tornado plus, we see the carbon peak, which is here. But if I mark this region and look for the finder, hafnium has a line there, selenium has a line there, strontium has a line there, yttrium has a line there, platinum has a line there, gold has a line there, silver, calcium, silicon, chlorine, all these elements have some lines there which overlap with that signal, and we are so much more sensitive for the other elements that we usually cannot tell it apart. So we do see carbon. So if you measure a diamond, we see carbon. If we measure on a plastic, we see carbon. But really, for analytical purposes, this is not the correct method. Then infrared or SEM, SEM maybe not so much, also because carbon coating. But yeah, so our detector is sensitive enough to detect carbon.
Yes.
But we cannot really use it for analytical purpose.
Yeah. Okay. The next question. Is it possible to accurately determine the depth of elements in a sample?
That's a very good question. That's a nice question. So the question, of course, is what is accuracy in this case? I would say no. I mean, it may be possible if you are working in a university and with some data crunching and some students who do this. We have never done it. We haven't, I think, even tried. Usually we would assume that we know what is on top, so and quantify the thickness of what is on top, and not so much really. I mean, that's a way of determining it, but just from the qualitative map, I wouldn't say that it is possible. But so there are some tricks. So our instrument, I never mentioned it before, but our video images is from top. So the camera looks from top, but our X-ray is on an angle of 50 degrees. So there's some. So the video looks from top, and the X-rays shoot from here. So, and from this misplacement, if you look very carefully, you may be able to actually determine the thickness or the depth in which something is lying. But that's very ambitious. Let's put it this way. It's an ambitious idea.
Okay. So the next question is from Partnono. I would like to ask the difference between EPMA and how about to detect carbon and lithium? I think you already mentioned before about the carbon. So yeah.
So EPMA is in principle, I think, double wavelength dispersive at the electron microscope. So EPMA has the higher spatial resolution, and it has the higher spectral resolution. But usually, before you measure, you need to select which elements you're interested in, because you need to align your spectrometers to the channel for aluminum and the channel for silicon and the channel for potassium and calcium, if you have a 4-channel EPMA. And anything which you didn't select, you are not measuring. So you need a second run to measure for titanium and for iron and for copper, and then another one for zinc and for lead and for all the other elements which may be in your sample. So with energy dispersive spectroscopy, not only with micro XRF, but always, you have more elements in your spectrum. I think this is the main difference, EPM versus energy dispersive in general. I think there was a second part which I already forgot. Carbon and lithium. I think so. Lithium really we cannot see. That's just so beryllium also. We stop at carbon. So boron, beryllium, and lithium are not in the measurable range of our detector. So we have a window still. It's a thin polymer foil, and this blocks the very light fluorescence. So also in an SEM, you would need a windowless detector for detecting these elements. And also with EPMA, you don't have any windows between your sample and your detector. And also in lithium, there's not many electrons. So it's a very light element. So and without the electrons in the lithium, we do not see fluorescence because as was said very early in the talk, we need electrons to change their positions in the atom to get fluorescence in the first place. And lithium doesn't produce fluorescence, which you could reasonably detect above any background. So this is really a part for EPMA. I mean, actually, at the synchrotron, or maybe with some very specialized instrumentation, you might be able to detect boron, beryllium with XRF instrumentation. But this is a tabletop instrument aiming to be to cover a very wide field of applications. So it's not at all specialized, and therefore, no, that's not possible.
Yeah. Okay. So the next question is actually we have another 4 questions. Okay.
For me, it's okay. Yes.
Yeah. Yeah. The time is enough.
Yeah, and it's early here.
Yeah, it's early. So the trend of food contaminant is increasing. Can this micro XRF detect some like fraud food, like contamination, the food? I think it depends.
So we do. Yeah. Yes. So are we talking about food?
Yes.
The fraud food.
Yeah.
So we have some projects with agricultural, so providers of nutritions for the field. I don't know the word at the moment. Where the thing you put on your fields to make the plants grow better, and some of them dope their product with some traces of say molybdenum, niobium, zirconium, really ppm, and we can detect these fingerprints in a food. I mean, maybe it's a problem with how I understand it, but I don't think you could tell an apple from an apple. Actually, well, you can detect different potato species. So there is some russet Burbank, I think, is a very famous potato species. This looks different in a map than other potatoes because the amount, or the relative amount of the nutrients, potassium, phosphorus, sulfur, they're different, and also the size of the islands. I think I showed the picture before.
Yeah.
Just here. Yeah. The size of these ATP containing islands, or the thickness here. So you can tell apart different sorts of potatoes, but I think that's not maybe a topic of fraud food analysis. So if by purpose, like some polices all over the world do it, that their own ammunition and the black powder which they use, they dope with marker elements to be able to tell whether a shot came from a police gun or some other gun. So if by purpose some marker elements are in the product, we are very likely to be able to detect it. So we have as I said, a very high sensitivity, especially in these rubidium to molybdenum range. Maybe I can show in the spectrum again. So this is the range. So for these elements, we are sensitive down to that's definitely 10 ppm range, because the rhodium, which comes from our tube, rhodium comes from our tube, directly excites. You see it's just above the absorption edge of molybdenum, and also niobium, zirconium. These are very effectively excited. So marker elements with these, also some, but also some rare earths, we do detect very small amounts as well. So if they are in the product by purpose, you can detect them. If you know, or if you are very sure that the strontium to zirconium ratio in your sort of food is 2 to 7, then you can check this against another product. And if it's not the same ratio, then you will see it. Just like the forensic people do it with glass analysis, just comparing intensities, not really quantifying it, but comparing the intensity ratios gives a good fingerprint. But it's nothing we ever tried. So fraud food is not our field of expertise. So we just started with the environmental, the biological samples with the M4+, which is 2 years now. And we haven't come to a point where this was something we tried.
Yeah. Okay. Sorry. So next question is, what is the maximum magnification that can be produced, and what is the largest pixel per meter area density that can be generated in mapping?
Okay. So in principle, so our spot is fixed at a size of, say, 20 micrometers. So that's the spot size which we have. And what we can do is we change the step size of our instrument. So 25 would be, oh, this instrument has a 20 micrometer spot size. So 20 micrometer would be really covering the full area with the spots. The smallest we can set is 4 micrometers. So this will then be, it's called oversampling. So we are measuring with a higher point density than we are actually resolving. But this leads to nice results. So here, for example, next slide, you see it. So this is an old BlackBerry phone. So it's some area measured. You see the ICs are still kept, but we can measure the gold wires. We can measure through the capping. And if we zoom in on, not really zoom in, but if we measure this with 4 micrometer step size, I think the whole thing was measured with 4 micrometers. So we get a better resolution for the, because we just see more, so how the intensity goes up and goes down on the other, I'm sharing my screen, sorry. So you see here an integrated circuit. And you see the bond wires, which are going really also in different levels of height. So going down here, and you see the curvature and everything. And you see this because we did lots of oversampling in the measurement. So there's no noise. And if there is noise, it's really flattened out by so many points. So 4 micrometers is the smallest step size, but usually, not usually. But you are then confined to smaller areas. You shouldn't, I don't think you could, maybe you could not even set a measurement over the whole area of the stage. So of the, see it here is this frame, 20 by 16 centimeters with 4 micrometer step size. You have hundreds of millions of individual pixels. And I think this will be too difficult for the software to handle. So we mapped the whole stage with 25 micrometers, and this is sufficient data. Usually, if you want to see small structures, then you need to know where you are looking for them. You don't go searching the whole large area for the very, very small structures. Okay.
Okay. So the next question, I think it was why you measuring. There's a question. If the sample is solid, it is better to use a high vacuum atmosphere. Is that so?
So if the sample is solid, it usually has no problems with the vacuum. So a rock, metal, or most industrial samples, they have no problems with the vacuum. If you have some plastic foam, this will not work, of course. If we are not measuring in a vacuum, we are restricted to elements above silicon. So the sodium, magnesium, aluminum, we will not be seeing if we are measuring in normal atmosphere. Silicon is also, the sensitivity is not very high anymore because the silicon is absorbed by the air, the signal, the signal of the silicon. So sulfur is almost unaffected. All the metals are virtually unaffected by any atmosphere. But if you would be classifying steels, for example, you sometimes need to know the silicon content, and then it's difficult. If you have steels which differ in the iron, chromium, nickel, copper, zinc ratio, then you don't need to pump down. And you even saved 2 minutes which it takes to evacuate. And then it's really open the door, place the sample, close the door, measure. So it would be very quick. Apart from that, so the atmosphere, so for the instrument itself, it doesn't matter. And for the measurement, it's really sensitivity for the light elements, which you change by evacuating the chamber. So question whether it is better or not, you see more. The more vacuum or the less air you have in your sample, in your chamber, the more you see. Also the argon, so there's 1% of argon in the air, and this produces a significant signal. So the X-rays excite the argon, and there is sufficient argon to really see the peak. If you have silver, for example, in your sample, you will have an overlap, and this may be difficult.
Okay. So the next question is it possible to use vacuum if sample powder? I think it's not.
Yeah.
Oh, okay.
So maybe I can quickly. There's the instrument. Is this higher? I go back to my instrument here. So it's just so this is pumping, blinking because I'm just putting the air back in. This is maybe the difficult part. So getting the air back in creates an airflow which may blow away your powder, but evacuating usually doesn't. It's like if you have a candle, you can easily blow it out, but it's very difficult to suck it out because there is no directed stream of air if you suck in air. And that's why if you evacuate the chamber, it's usually, there is no direction and your samples won't move. If you go back in, you get so the inlet for the air is at the very bottom right corner. And we are thinking about putting extra diffusers in to prevent directional flow. But for example, measuring powder in a cap is not a problem. And we sometimes, or more than once, measured powder just on the table. So it's not per se a problem. Liquids a little bit more a problem because they tend to evaporate in a vacuum. But powders usually works fine. Sometimes we even place them on our plastic foil suspension because then we have less background. And the main problem is the vibration from the pump. This starts to, this membrane starts to move. And this is maybe a problem, but if you put them in a small cup, you can measure powders easily in the vacuum.
I see. Okay. Next question is, what is the micro XRF capable to observe a metallic paste of steel within its microstructure, like observation of paste in the steel using EBSD?
The EBSD? So we are, of course, we don't have the same resolution, the same spatial resolution. In a steel,
sorry, I share.
In a steel, so we do see, maybe again, I think I do have some pictures to that. In the part where this is an old talk, I was talking about quantification. I need to share the correct screen. So these are the steel samples I showed before. So the one with the polished surface. And here, this is cobalt, chromium, and iron in red, cyan, and yellow. And you see that there are some which have structure at the surface. Others where you do not see it so much, but and these freckles are diffraction peaks. So even though the elemental composition does not change, do I have a spectrum for it? Sorry, not here. Maybe, yeah, there. So we do see diffraction peaks here and there. We had one before with the trying to find uranium. And also here, there is one which would be overlapping with lead at 10 keV. There is one here which may, calcium is not a problem, but this would be mimicking a calcium peak. There's something here between iron and cobalt. Usually in a steel, so for chromium, iron, and nickel, it's not much a problem because these are the main elements. But if we go to the traces, this overlap becomes significant. So these will not be a stainless steel, but maybe an iron alloy. Otherwise, the chromium wouldn't stick out like that. So we see structure of the metal. Maybe it's comparable to EBSD, but our resolution is much coarser, and we cannot do it quantitatively. We only see that there is crystals, and we cannot make use of it so much, at least not at the moment, and maybe it will be taking some time before we can. With the two detectors, in theory, it should be possible to identify the diffraction peaks. And yeah, since we know the composition at that position from our spectrum, we could maybe calculate orientations, but we cannot do it at the moment. At the moment, diffraction is an artifact, but let me scroll here. We can sometimes make use of it as well. So this is two steels. Iron molybdenum, and this is more or less only iron, welded together. And this is looking for some diffraction structures. So these F1, 2, 3, 4, 5, 6 here means it's a free region in the spectrum where I can display the intensity distribution. And then I see the crystallites, not the elements, but the crystallites. And I see that these crystallites are always perpendicular to the surface here. And they are larger inside than at the surface. And this is really how crystals grow. Larger crystals grow where the cooling process is slower. These directly at the interface, the heat was transferred to the steel, so these cooled very fast. That's why it's only small crystals. And in the center, we have the larger crystals because it cooled slower. And also the direction of the heat gradient is visible, so it's perpendicular to the surfaces here. So we can make analytical use of the diffraction, but we cannot say this is oriented 110 or something, but it's there. You can only tell it's there. And its size, if necessary.
Okay.
But yeah, I don't know whether this really was the question, but in a steel, we get additional information. So on structure, on substructure. Usually in copper alloys, we see that they tend to become inhomogeneous on the micrometer scale. So the lead the tin and the copper, they form some islands.
Okay.
So this side of inhomogeneity you start to see with the micro resolution, but you would also be seeing it with an SEM, of course.
Mm-hmm. Okay. I think we have last question from automotive. Sorry, yeah.
Mm-hmm.
So I think, yeah, how to use a micro FTIR. Sorry, I think he misunderstanding. This is a micro XRF
Mm-hmm.
for failure part of or crack analysis on polymer material such as fiberglass, PP. Can be micro XRF show the detail of crack area better than SEM?
Maybe yes. So with the plastic part, you usually have the problem that it's not conductive, and then you have problems with analyzing it with an SEM.
Mm-hmm.
We have more the problem that the elemental contrast is not really high. So I don't have an example now here, but we would using then the scattering. Plastic has lots of scattering and can maybe where is my table? Quickly, maybe realign. There's a PVC mat between the samples and also the PCB. Maybe we could have seen it. So this is now the PVC here of the which we use to prevent the samples from slipping back and forth. If I press, oh, it's an area scan. It's not what I wanted. So let me quickly change to the point mode and start the measurement. So this number 31 here, now in blue, was the granite tile. And
sorry,
in red,
we cannot see.
Again. Sorry. Okay, in blue, we have the coating, actually. So nickel copper, so metallic, so to say. And now we have the PVC in red, where, of course, so I see now the argon peak because I haven't evacuated. Oh, I did evacuate. So chlorine it is. And calcium, filler element in plastics. So PVC, we do see the chlorine, of course, and we see lots of scattering. The light matrix here produces a lot of scattering background in our measurement. And excuse me, sorry. And in a crack, we would see differences in the scattering. So not a direct analysis, but we could visualize cracks. And maybe if it's related to any elemental change, then we would be seeing that as well. But the plastic is very transparent for our X-rays. And therefore, am I muted now?
Oh, no. Okay.
Oh. And now, so no, not muted. Okay. Yeah, we would be using the scattering. So this is the high energy scattering, which is sensitive into the depth. So interesting for cracks. And then we also have overlapping with the chlorine, the low energy scattering of the rhodium. We do not see it as much now because such a high chlorine signal, but there is the rhodium scattering in low energy as well, which is surface sensitive. And we could most likely see the cracks from that. But I don't know what sort of analysis ultimately would be the question. So quantifying its depth or size, or I don't know. There will be restrictions, so it's not,
Okay. Okay, I think that's the last question. Yeah. So, do you have anything to deliver to us about micro XRF or?
Me?
Yeah, it's enough.
No, it's just as a general wrap up.
Yeah.
So I mean,
Okay.
I'm a bit biased, but this is a very nice method because what we do here, if you find something on your way to work on the street, you can just place it in here and check what it is. Sometimes it's interesting, most times it's not. But yeah, it's very quick method to get to know the samples.
Okay.
And
Sorry.
I like it.
Mm-hmm. I have one question again. Sorry, this is last. Okay, what is the maximum voltage allow in order to avoid burning of the sample?
Excuse me, please again.
The maximum voltage allow in order to avoid burning of the sample.
We have this burning of the sample, which you know from the from the large instruments, is mainly because you have so much beam load, and also your sample is a glass bead. So you see in these glass beads or in the what's hexafluoride. So in these diluted samples, which is glass-like, you see this coloring. We don't put that much power onto our samples.
Yeah.
That's why we don't have the effect. And we do see coloration in glasses. So if we measure for, say, 5 minutes on the same position on a glass, there will be some color ring. But if you just place the glass on your windowsill and the sun shines onto it, this vanishes over time. So this is not permanent damage. So we don't have the problem of burning our samples. Yeah. I think for some biological samples, it may be a problem, but we have, so what we measured until now did not have a problem with the radiation. The vacuum is a bigger problem for the organic samples because they dry out much faster. Yeah. And that's why we have the helium flow in the M4+, which you could also replace by a nitrogen flow or any other gas, just to have something which is still, prevented.
Okay. Yeah, okay, I think that the last question. Okay, thank you very much, Volk. It was very well presented and very clear demonstration. Show all the type of sample that can be analyzed with micro XRF, how micro XRF work, how to use the software, and it's very interesting and clear. And thank you very much.
You're very welcome. Thank you for the invitation.
Okay, I think sepertinya kita sudah di penghujung acara. Bagi pertanyaan yang belum bisa kami jawab karena keterbatasan waktu, kami akan menjawab terpisah melalui email. Thank you very much, Dad. And
You're welcome.
Thank you very much, Dad. Yeah, I deeply appreciate for the enlightening micro XRF presentation, and I hope we can have another webinar together, or maybe it will be nice if we can have direct meeting. Let's hope this pandemic is over. Okay. Terima kasih atas waktunya, Bapak Ibu. Semoga webinar kali ini dapat bermanfaat. Mohon maaf jika masih banyak kekurangan dari kami untuk evaluasi kami terhadap acara webinar ini, dan untuk selanjutnya kami harapkan Bapak Ibu semua dapat mengisi feedback form di bit.ly/fb-microxrf. Jangan lupa ikuti Instagram kami juga di Dynatech INT untuk update kegiatan-kegiatan lainnya. Untuk sertifikat dan recording akan kami kirimkan melalui email. Jika ada informasi yang dibutuhkan, mohon jangan sungkan untuk menghubungi kami, bisa melalui website di www.dynatech-int.com atau bisa hubungi langsung di nomor berikut. Saya Tiffany dan tim PT Dynatech International dengan broker pamit undur diri. Mohon maaf jika masih banyak kekurangan. Silahkan untuk memberi masukan di feedback untuk kami lebih baik lagi. Terima kasih banyak atas partisipasi Bapak Ibu sekalian. Stay safe and stay healthy. Wassalamualaikum warahmatullahi wabarakatuh. Thank you semuanya.
Terima kasih semuanya atas kehadirannya.